Hello everyone, Mrs. Hanson back again. In our last lesson we brought conclusion to the study of gases. We're going to turn our attention into the other two phases of matter, liquids and solids. And remember that we said their qualities that made them very different from the gases is that they had very strong intermolecular attractions. They're being held together. Of course, the solids being held together in very fixed, rigid positions. But the liquids are also held very compactly tight. I mean, they do flow past each other, but they are very close to one another. So close that they can exhibit an intermolecular attraction or an intermolecular force between the samples. This section is going to study the three different categories, three different kinds of intermolecular forces. You'll see that I'm going to abbreviate that IMF, intermolecular forces, and how they affect physical properties such as boiling points and melting points of molecules. Let's define the intermolecular force as the attraction between molecules. It is not a true bond, but a mere attraction between two molecules, so close together that molecules can influence the behavior of another one close by, a nearby neighbor. In order of increasing strength, we will talk about London dispersion forces, which we are saying are the weakest of these intermolecular attractions. A dipole-dipole interaction would be our second category, and then the strongest of all intermolecular attraction is known as a hydrogen bond. When we see the strength of these intermolecular forces, it's going to determine whether a compound will have a very high or a very low melting point. Will it have a high or a low boiling point? Is it a solid, a liquid, or a gas at a given temperature? Of course, solids tend to have very strong intermolecular attractions, holding them so close together in a fixed, rigid position. As we explore, we're going to talk about London dispersion forces, sometimes just simply known as dispersion forces. Then we'll move to dipole-dipole, and then finally look at hydrogen bonding. Let's look at the London dispersion force first, or just simply call it a dispersion force. We're going to define these dispersion forces as very weak interactions just based on being close to one another in a moment in time. When two molecules are close to one another, they may interact in terms of their electron density. When they do so, they create what are called temporary dipoles, just a quick fleeting moment of time where the electron cloud, remember that's just kind of a squishy cloud, can create an area that has a positive and a negative attraction. Here's an example of a molecule that comes so close together. Remember that like charges repel, opposite charges attract. And we're just showing is intermolecular attraction between two molecules based on those opposite charges. All covalent compounds exhibit London dispersion forces. And the bigger the molecule is, especially the longer the chain is on that molecule, the more opportunity they have to set up these attractions, and therefore the stronger the intermolecular force becomes. If I think about just an example, let's show a picture of a helium atom. Remember, a simple model of helium would show two positive protons, two neutral neutrons in the nucleus, but the positive charge inside the nucleus. And then we had two electrons in the first energy level around it. When two helium atoms become so close together, their charges can influence one another, that the nucleus from this atom can actually draw the electrons of the other atom towards itself. And when it does so, it introduces this very temporary dipole interaction. So here I have a region that is very rich in electron density. Here I have a region that's very poor in electron density. Opposite charges attract. Remember that this means electron rich, and this symbol means electron deficient. And it's just influencing the the electron cloud for a moment in time just because these atoms came so close together. The nucleus of one atom attracts the electrons from the other, and you'll see just an unequal distribution of charge for a moment. Instantaneous dipoles. That's how I want you to think about a London dispersion force. It's just a moment in time where one electron cloud is getting influenced by another atom's nucleus. The larger the molecule, the more the dispersion force sets up. So these London dispersion forces, as I lost my screen, these are all molecules will exhibit London dispersion forces. Now, those are the weakest. Let's look at a second category of intermolecular attraction known as the dipole-dipole interaction. Dipole. Remember back from our chapter 4 how we defined the term polarity is just an unequal distribution of charge. In a dispersion force, it was temporary. But in a dipole-dipole force, these are permanent dipoles. So that's based on the polarity of the molecule. All polar molecules exhibit dipole-dipole interactions. Let's take a look at drawing a simple compound such as formaldehyde. Notice here on the oxygen, the lone pairs of electrons, making this a very electron-rich area. And of course, the hydrogens down here, a very positive electron deficient area. When two molecules of formaldehyde come so close together, they can form an attraction between opposite charges. Let's draw on our notepad the interaction between two molecules called formaldehyde. Make sure you're pointing the oxygens. Let's just draw this together. Here would be the formaldehyde, where the oxygen, who is very electron rich, is being attracted to the carbon on the other molecule, who is very electron deficient. And we actually show these interactions with kind of these dashed lines. It's not a true bond, but an interaction sets up between them. So just draw that as a dashed line representing an attraction. Not a true bond, but a very strong attraction. So any polar molecules will set up a dipole-dipole interaction just based on opposite charges. Remember, a dispersion force, sometimes called a London dispersion force, is a temporary dipole, whereas dipole-dipole interactions are permanent dipoles. So it's a polar molecule. They will not have, the polarity of the molecule is built into its structure. So let's take a peek at this question here. Draw the individual dipoles of two HCl molecules and show how the dipoles are aligned in a dipole-dipole interaction. I just want you to think of this word as just representing a polar molecule. Remember, like a bar magnet. A bar magnet has a positive terminal and a negative terminal. The same structure has two different regions of charges. One is more negative, one is more positive. That's what's referred to as a dipole. So if a hydrogen is bonded to a chlorine, remember hydrogen with its 1 valence electron will form one bond. Chlorine with its 7 valence electrons will form one bond and creates an octet. Clearly we see this is a very rich electron area and this is a very deficient electron area. The electronegativity of chlorine is pulling the electron density towards the chlorine, a polar bond and a polar molecule. Well, the chlorine from one hydrogen chloride molecule would be attracted to a hydrogen from the other hydrogen chloride molecule, and we set up not a true bond, but an interaction called a dipole-dipole intermolecular force. And so that's what we just drew. The positive region of a hydrogen is attracted to the negative region of a chloride, and you could draw these all day long. HCl would be attracted to this compound, and we see all kinds of interactions setting up. So a dipole-dipole interaction exists between two molecules that are polar in nature. The third and most powerful intermolecular attraction is called hydrogen bonding, and it's a very special criteria of a polar molecule. Hydrogen bonding occurs when a hydrogen atom is bonded to an oxygen, nitrogen, or a fluorine. So here's H to N, here's H to O, here's H to F. Now I want you to think about where these guys are located on the periodic table, right? They're right in on row 2 in period 2. You'd have nitrogen, right? So if you just remember your elements, you go carbon, then nitrogen, then oxygen, then fluorine, and then of course you reach your noble gas. This guy here is the most electronegative element. It can pull electrons towards itself very strongly. The next most electronegative element is oxygen. The next most electronegative element is nitrogen. These are the three elements that are so electronegative. When they bond to hydrogen, it creates a very, very strong intermolecular attraction. So to have the criteria to make hydrogen bonding in the same compound, in the same molecule itself, you have to have an H to an N, an H to an O, or an H to an F in the same molecule. Then between those molecules, we set up hydrogen bonding. So for example, when we would draw the Lewis dot structure for water, we saw that this was a very rich region of electron density on the oxygen, and that the hydrogens were very electron deficient, giving it a partial positive charge. To be electron rich makes you negative overall. To be electron deficient makes you positive overall. So this oxygen on one water molecule would be attracted to a hydrogen on a next water molecule. And again, we would just draw those with this dashed line, showing that that would be the representation of a hydrogen bond. The hydrogen bond is between molecules. And remember that word bond, it might be deceiving because it's not a true bond, but it's an attraction between molecules. All right. So the strongest of those three types of intermolecular attractions, just to remind ourselves, the weakest would be dispersion forces. All molecules have dispersion forces. Those are temporary dipoles. Just a moment in time where the electron cloud gets upset, gets redistributed, and creates temporary dipoles, but it's a fleeting moment. The second we said, a little bit stronger, is dipole-dipole. Only polar molecules will exhibit dipole-dipole interactions. You must be polar. And then, of course, the strongest is a polar molecule that's in the compound, has an H to an N, H to an O, or an H to an F. So it's polar, but it also contains one of those three special bonds, and that's the strongest interaction of all, based on the electronegativity difference of those N, O, or F atoms. And this is a nice chart to kind of clarify what we just wrote. London dispersion forces are very weak. They're exhibited by all molecules. An example, well, any molecule, such as methane. Methane is a non-polar molecule. It has nothing exciting at all in that structure. H2CO could exhibit a London dispersion force because all molecules exhibit London dispersion forces. And so if I draw H2CO, we could see that this is polar. So it also exhibits not only dispersion forces, but it would exhibit dipole-dipole as well. Whereas if you're nonpolar, you only have dispersion forces. And then the last one we drew was a water molecule, which has dispersion forces because all molecules do. It's polar, so it's also a dipole-dipole interaction, and it contains within the same compound, it meets the criteria of hydrogen bonding. So you could see water has all three intermolecular attractions. Nonpolar molecules, only dispersion. Polar molecules, dispersion and dipole-dipole. And then if the polar molecule meets the criteria of hydrogen bonding, it would contain all three, a very, very tight, sticky molecule. Let's try some out. What types of IMFs, intermolecular forces, what types of IMFs are present in each of these compounds? So let's try to draw them out. Here's HCl. Here's C2H6. Knowing that carbon needs 4 bonds, we'll satisfy carbon's need for 4 bonds by placing those hydrogens around them. And then ammonia, remember nitrogen, in group 5A, it forms 3 bonds and a lone set of dots. So there's our structures. In letter A, in letter B, in letter C. Well, let's just tackle them one at a time. The London dispersion force. London dispersion forces are temporary dipoles exhibited by all molecules. So granted, I'm going to put London dispersion forces for all of them because all molecules will always exhibit London dispersion forces. And would it be all right if I have London dispersion forces? London dispersion forces. We'll just abbreviate that. Now, what about dipole-dipole, which is the next strongest? And remember that only polar molecules exhibit dipole-dipole. So we're looking for polarity. Well, I recognize that this HCl is a polar molecule based on the uneven distribution of electron charge. This hydrogen chloride is polar, and so therefore it will exhibit dipole-dipole interactions. How about the letter B? Anything interesting in that boring carbon chain? Remember that a carbon to carbon is nonpolar, a carbon to hydrogen is nonpolar, and the overall molecule is completely symmetrical. There's just an equal distribution of charge in all directions. So this is a nonpolar molecule, and therefore no dipole-dipole interactions. Right here on the nitrogen is a very electron-rich area, making these hydrogens partial positives. So this is a polar molecule, an unequal distribution of charge with that lone pair of electrons on the nitrogen. So that means, yes, it meets the criteria of dipole-dipole interactions. All polar molecules will have dipole-dipole. Now let's check out the last one, called hydrogen bonds. To meet the criteria of a hydrogen bond, you must have in the molecule an H attached to an N, or an H attached to an O, or an H bonded to an F. Do you see any of our molecules that meet that criteria? Well, in letter A, hydrogen is present, but it's not bonded to an N, O, or F. So no hydrogen bonding. Letter B is a boring nonpolar molecule, so no hydrogen bonding. And in letter C, look at, we have H bonded to an N 3 different ways. So there's 3 opportunities for hydrogen bonding there. So ammonia exhibits all 3 intermolecular forces. So ammonia with all 3 has the highest intermolecular forces. And of course, B, which was boring old ethane, has the lowest with just one interaction. Now that's going to give us insight into something about like melting point and boiling point. The stronger these bonds are, the stronger the IMFs, the molecules stick together. Right? They're very, very attracted to one another. So these ammonia molecules are really held tightly together. So it's going to take a whole lot of energy to disrupt and cause those molecules to separate to force a boiling. You try these. Identify the types of IMFs present in each molecule. Pause your video and give yourself some think time. Really think this through. Start by drawing structures even. Come back when ready. Welcome back. Chlorine bonded to chlorine, that's a non-polar molecule. It's an equal distribution of charge, so it's non-polar. That tells me that the only type of intermolecular attraction would be a London dispersion force. How about letter B? Here you have H bonded to carbon, triple bonded to nitrogen. With that HCN, we have a polar molecule with an unequal distribution of charge, so it is polar. So all molecules have dispersion forces, that's a given. Since this is polar, it also meets the criteria for dipole-dipole. But it does not exhibit hydrogen bonding because there is no hydrogen directly attached to a nitrogen, oxygen, or fluorine. It's not okay to say they're in the same compound. They have to be directly attached, and that is not the case here for letter B. Letter C is HF. Well, all molecules exhibit dispersion, so that's a given, a temporary dipole. This happens to also be polar with the unequal distribution of charge around the fluorine compared to the hydrogen, a very electronegative bond there. So it also exhibits dipole-dipole. And it does indeed meet the criteria for hydrogen bonding with an H directly attached to a fluorine. Here's CH3F. Nope, CH, oh, H3Cl, okay. 3 H's and a chlorine. Got it. So here's your structure for letter D. Notice that this is a very rich electron area, making these hydrogens electron deficient. So this is a polar molecule, an unequal distribution of charge. We know that all molecules have dispersion forces. Since this is polar, it would also have dipole-dipole interactions, but it does not have a hydrogen attached to an N, O, or an F, so it will not exhibit hydrogen bonding. Letter E is a hydrogen bonded to a hydrogen. Well, that's pretty simple. It's a boring molecule. All molecules have dispersion forces, but it is non-polar, so it will only have dispersion forces, and that's it. How'd you do? Did you work ahead for this one as well? If not, pause the video and ask yourself which one of these has the stronger intermolecular force. Have you given yourself think time and come back? Well, the secret lies in being able to draw the Lewis dot structure. You know carbon needs 4 bonds, so carbon dioxide has double bonds in it. Therefore, we have a symmetrical molecule that it has an equal distribution of charge, so that it's kind of a nice boring molecule, really. And here's water. You know, oxygen has to have 2 bonds, 2 sets of dots. And so here, Carbon dioxide would have dispersion forces only because it's nonpolar, perfectly symmetrical molecule, just two domains, and each one of them lead to the exact same atom, an oxygen. So dispersion only. Whereas water not only has dispersion forces, this is polar, so it has dipole-dipole, and it meets the criteria for hydrogen bonding. Clearly, water is going to have a higher intermolecular attraction, stronger forces. Because it has stronger forces, we would expect it to have a higher boiling point, higher melting point, and so forth. How about letter B? Carbon dioxide, well, we just drew that. So here's our CO2 again. We know that it's nonpolar. So it will only have dispersion forces. And we're comparing it to HBr. Well, HBr is a polar molecule, so it will have dispersion forces because all molecules do, as well as dipole-dipole. So clearly HBr would have more intermolecular force. Now let's compare HBr to HOH. We said HBr is polar, so it has dispersion and it has dipole-dipole. And we said that water meets the criteria for dispersion, dipole-dipole, as well as hydrogen bonding. So therefore, the water will have greater intermolecular attractions. Now, what might not be so obvious is comparing helium to neon, because these two atoms, well, they're not going to exhibit polarity. These are non-polar, right? They're just a single atom. So the only type of force they have is dispersion forces. So what would influence the attraction between these? Remember, the dispersion force increases with increasing molar mass. And I could just say increasing size or how heavy it is. The heavier molecules, the bigger the atoms, the greater the intermolecular attractions. So since neon is the bigger atom, it would exhibit larger dispersion forces. It has a squishier cloud, right? Here's a little neon atom. Here's a little helium. And bigger than that would be the neon, so it has a squishier cloud, if you will, more electron cloud to it. Therefore, it has a greater influence to electron motion. So neon exhibits the greater dispersion force. Now, these intermolecular attractions give rise to these physical properties or qualities called boiling points and melting points. Let's define the term boiling point is simply the temperature at which a liquid is converted to the gas, right? So it's a phase change. A liquid converts to a gas. When that happens, evaporation is the term for that. The boiling point is the temperature at which we see the conversion. Of course, the melting point would be a solid converting to a liquid. What temperature do we see the phase change at is known as a melting point. And if we have really, really strong intermolecular attractions between molecules, it's going to take more and more and more energy to cause that phase change to occur, because attractions hold molecules together. So if attractions, strong attractions, hold molecules together, we want to separate them, right? A liquid has to separate to form gases, and a solid has to separate to form its liquid phase. So you have to overcome that strong intermolecular attraction with more energy. So compounds with dispersion forces only have very low melting points and boiling points. Compounds that have dipole-dipole interactions lie in the middle, And of course, if you have all three criteria of intermolecular forces, you're going to have very high boiling points and very high melting points. So the increasing strength of the IMFs directly affects the energy needed to cause the change of phase. And let's kind of look at this example. These are two compounds that really have a comparable molar mass. This molar mass of methane would be 16 grams, a carbon added to 4 hydrogens. Here, this molar mass of water is 18 grams per mole, very comparable in terms of weight. And you look at the significant difference in their boiling points and melting points. We know water boils at 100 degrees Celsius. Methane, which is a gas at room temperature, its boiling point is listed at negative 162. Well, remember, this is a boring molecule, right? It's not got a lot going on. It's a non-polar molecule. So it only has dispersion forces, just temporary dipoles, very weak intermolecular attractions. Water not only has dispersion, it has dipole-dipole, and it has hydrogen bonding. It meets the criteria for all three intermolecular attractions. So it's a very strong attraction. Therefore, it's going to take a whole lot of energy to separate water molecules because they're just so strongly held together. The stronger the intermolecular attraction, the higher the boiling point. You can compare the size of molecules as well. Propane is a 3-carbon chain. Carbon 1, 2, 3. Now notice here, simply by lengthening the chain to a 4-carbon unit, we've increased the boiling point. So again, both are non-polar molecules, so they both exhibit dispersion forces only, but heavier molecules require more energy to get them to boil. So the longer the carbon chain, the heavier the molecule, the stronger the dispersion forces. You're going to need more energy to cause those molecules to separate and start to boil away. Determine the order of the melting points. What would these look like from lowest to highest? We have ammonia, methane, methanol, and chloromethane. Remember ammonia? We just drew it a little bit ago. It had a set of electron dots on that nitrogen, right? Nitrogen group 5A, so 3 bonds and 1 set of dots. This means that it has dispersion. It always does. It is polar, so it has dipole-dipole. And it meets the criteria for hydrogen bonding. Very strong intermolecular attractions. Here's the methane molecule, which you see is kind of that boring hydrocarbon chain. So this is dispersion only. Here is a methanol drawn out for us. Now this is polar, isn't it? So all molecules have dispersion. This is polar, so it's dipole-dipole. You see this very rich electron area, and it meets the criteria for hydrogen bonding, doesn't it? It has an O attached to an H right there. And then this guy, it has dispersion. All of them do. It is polar, so it has dipole-dipole. Now that we've got all the intermolecular attractions figured out, the lowest melting point has the weakest attractions. The highest boiling point, or melting point, has the strongest IMFs. All right, so the weakest is easy to figure out. That's methane, CH4, only dispersion forces. And even in the middle, chloromethane, CH3Cl, it has dispersion and dipole-dipole. Now, between A and C, both of those exhibit all three. So how do we tell? go by molar mass. Who's the heavier compound, right? So the dispersion forces will increase with the mass. So here's a carbon, hydrogen, there's 4 of them there, and oxygen is 16. Clearly you can see 12 and 16, that's 10, 11, 12. That molar mass is 32 grams. This guy over here, the molar mass is 17 grams. You can just see by the size of the molecule itself, alcohol is bigger, right? That methanol. So it will indeed have the highest boiling point, and ammonia would be here, simply because this is the heavier, right? And that bigger molecule is going to require more energy. How'd you do? Now, it's just kind of intuitive to say the more exciting, the more strong those electrons are being held together, the molecules are sticky to one another, it's going to create more energy to force them to separate and change phase. Try some more. Which compound in each pair has the higher boiling point? Letter A, carbon with its 4 bonds. These are all nonpolar molecules, so they're both only exhibiting dispersion forces. So to tie break, you need the bigger molecule. The heavier molecule will have the higher boiling point. Here's letter B, C2H6. Versus CH3OH. Now, seeing these, you can tell that this is nonpolar, so this will have dispersion only. Whereas this guy is not only polar, so it's going to have dipole-dipole, but it also meets the criteria for hydrogen bonding, doesn't it? I see an O directly attached to an H. That one was easy. HBr or HCl. So these both exhibit dispersion. They're both polar, so they have dipole-dipole, but there's no hydrogen bonding because the H is not attached to an N, an O, or an F. So to determine this, it's the heavier molecule. A bromine is heavier than a chlorine, so therefore it will need more energy to get that bigger atom to boil. And here's C2H6 again versus CH3Br. And what did you pick? Well, this is nonpolar, so this is dispersion only, where this is polar, so it has dispersion and dipole-dipole. So therefore, that's the stronger intermolecular attraction, and therefore, it would have the higher boiling point. Way cool. Let's define the term vapor pressure and talk about exo and endothermic processes in phase change. Evaporation is the conversion of a liquid to a gas. That phase change where the liquid turns to a gas is known as evaporation. In order for a liquid to turn to a gas, it must absorb heat. So we said that this was an endothermic process. Delta H would be a positive value. So thinking about just absorbing heat energy. Condensation is the opposite, isn't it? Condensation says, let's take a gas and turn it back into a liquid. And in doing so, you release the extra heat. Therefore, this is an exothermic process. Giving off heat to the surroundings is exothermic. Absorbing heat from the surroundings is endothermic. So to force the liquid to turn to a gas, it's going to require heat. And to force the opposite, it releases the extra heat. Endo and exothermic processes. In the liquid state, there is a dynamic equilibrium between the liquid phase and the gaseous phase. And when you see a vapor pressure, just think about that gas pressure pushing down on the surface of the liquid. The vapor pressure is defined as the pressure exerted by the gaseous phase on the surface of its liquid. Now, think about that. The more and more and more gas you have above the surface of its liquid, the more push you would have down, and that would increase the vapor pressure. So as I begin to increase energy of the system by raising the temperature, more of the liquid molecules can escape as a gas, and that's going to increase the vapor pressure. So when a solution finally boils, the liquid is at the temperature. That's the definition of boiling point, when the liquid is finally at the temperature which equals the vapor pressure of the atmosphere. And this was our standard pressure, 760 mmHgs per millimeter mercury. A boiling point is defined as when the vapor pressure equals atmospheric pressure, the solution will begin to boil. So, how does intermolecular forces affect vapor pressure? Remember, the stronger the attraction that the liquid has, they're going to stick together. So high intermolecular attractions kind of prevent the molecules from evaporating, and thus they'll have low vapor pressure. Strong intermolecular attractions keep them in the liquid phase. And therefore, you have very few molecules in the gaseous phase, and so you don't have very many pushing down. So this is a very low vapor pressure. But consider a nonpolar molecule, a very boring molecule like methane. This has very weak intermolecular attractions. So that means these molecules are not being held together very strongly and are more likely to escape from the liquid to the gaseous phase. And therefore, more gases up above are going to have a higher vapor pressure. So if you have low intermolecular forces, you have a high vapor pressure. If you have very strong intermolecular attractions, you have a very low vapor pressure. Remember, the more gaseous molecules, the higher the vapor pressure, the more pushed on the surface of the liquid. So if you have very strong intermolecular attractions like a water molecule, remember, they have dispersion, they have dipole-dipole, and they exhibit H bonds. That's going to hold them in the liquid phase. Holds them here. And then very few escape. So that creates a very low vapor pressure. So which compound has a higher boiling point? Let's just determine this by structure. H2O versus H2S, water versus hydrogen sulfide. Well, we know that all molecules exhibit dispersion forces. We know that polar molecules exhibit dipole-dipole, and these definitely are both polar molecules. But this meets the criteria for hydrogen bonding, whereas the H2S does not. So therefore, this has higher intermolecular attractions, intermolecular forces. So which has the higher boiling point? Well, water does, because it has the highest intermolecular attraction. It's going to take the most energy to break the attractions to force the phase change. Highest boiling point is the highest intermolecular attractions. Who has the higher vapor pressure? Well, that's H2S, because with the weaker intermolecular attractions, that's supposed to say pressure, the molecules can escape the liquid phase and form a gas. Oh, slow down, Linda. Weakest IMF said the liquid to the gas phase, that's the change of phase, will occur more readily. And therefore, since we have more gas above the surface, you'll have a higher vapor pressure. Which compound in each pair has the higher vapor pressure at each temperature? Now just interpret that. The highest vapor pressure is accomplished by asking yourself, who has the weakest IMFs? Strong IMFs keep the molecules in the liquid phase. Weak IMFs allow the liquid to turn to a gas and thus raise vapor pressure. Now that's the logic of this question. Find the weakest vapor pressure. In letter A, you have a non-polar molecule, quite boring, methane, versus ammonia. The highest vapor pressure is the more boring. This is dispersion only. How about B? Here you have methane or ethane, your hydrocarbon chemistry from next term. So again, this is dispersion only. So you're going to go by molar mass, right? This has the higher dispersion force because it's heavier. Higher meaning stronger. That would be a better word than saying higher. Higher molar mass would make it a stronger dispersion force. And so therefore, this guy would have more vapor pressure. It has the weaker intermolecular attractions. And letter C, you have a nonpolar molecule, C2H6, versus a polar molecule that has hydrogen bonding. So this is a very strong intermolecular attraction. It actually has all three, doesn't it? Dispersion, dipole-dipole, and hydrogen bond. So clearly the more boring molecule is the ethane, and it would have the higher vapor pressure. Another quality of a liquid that can be explained through intermolecular attractions is viscosity and, again, surface tension. Let's just take a look at viscosity first. We're going to define the term viscosity as a measure of a fluid's resistance to flow freely. Viscous liquids feel thick, like syrup is a very viscous liquid. Compounds with very strong intermolecular attractions tend to be more viscous. Substances composed of large molecules tend to be more viscous. Well, that's because their dispersion forces are stronger. So molecules being held together to create a very thick liquid are known as viscous. Viscosity is a measure of that fluid's resistance to flow freely. Let's say water, of course, flows quite freely. Surface tension is defined as a measure of the resistance of a liquid to spread out. So in other words, look at this little water bug on the surface of the actual lake or whatever it's in. The water itself, if you think about it, it has a high resistance to spread out. In other words, it will bead up instead of lies flat. That's due to surface tension. The ability of the resistance to the spread out. So the water molecule actually forces them to stick together and causes a bead. And that's just kind of known as surface tension. And that's really the reason why we can float things on water. The stronger the IMFs, the stronger the intermolecular forces, The stronger those surface molecules are pulled down towards the interior of the liquid, and that creates a surface tension. Water is notorious for having a very high surface tension. Not only does it have dispersion, it has dipole-dipole, as well as hydrogen bonding. And when small objects seem to float on the surface of water, they're just being held up by that intermolecular attraction, creating surface tension. You can take a straight pin and float it on the surface of a water. However, if you pierce the surface of the liquid, it will drop right through. So you can float it if you just lie it flat, but if you pierce the top, it will sink. Would you predict the surface of gasoline, composed mostly of carbon to hydrogen atoms? Well, you might not know this, but gasoline is composed of octane. Octane is an 8-carbon unit. Octane is 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. And of course, carbons need 4 bonds. So those are all the hydrogens satisfying 4 bonds of carbon. You would see C8, H16. There's 18 hydrogens in there. And I just am not drawing them all. So there's octane. Would it be higher or lower than the surface tension of water? Now this is interesting because this is a very long molecule. It's a very heavy molecule. So it would have very strong dispersion forces. No doubt about it. It would have strong dispersion forces. But what about water? Well, it has dispersion because all of them do. We know it has dipole-dipole because it's polar, and it meets the criteria for hydrogen bonding. So this non-polar molecule, even though it's long and has strong dispersion forces, it does not have the same strength of intermolecular attractions as a water does, and therefore water would have a higher surface tension. Now think about it. Things don't float on gasoline. Things float on water due to the surface tension, really because of its hydrogen bonding. And let's stop our video here. We've made it through the gaseous phase. We've made it through the liquid phase. We'll take a little break. And when ready, come back and we'll wrap up some solid phase chemistry.